All right, so up and running. Just a little addendum to the last video. I was thinking about one of the calculations and something popped into the head, and I just want to show you that. Tie this to what we were talking about in the little conceptual chat we had about conversion process and related rates. So at the very end of the video, I'll make that connection. But while I was thinking about that, I think it's still very important to try to get a feeling for the chain rule. And that takes time. That's not going to happen overnight. To really get a solid feeling for the numerics and what's going on conceptually, I think it's very difficult. So I want to put two videos in front of you. One is the chain rule through the lens of integration. I think we've done enough area under the curves now that we can begin that conversation. So I'm going to elaborate on that. And I'm also going to be talking about the chain rule, the playlist. I think it's in the calc playlist. I use y equals sine of x squared. And I'm going to something here. Let's click on that. Get that off the screen. So I think I used at x equals 3. I just wanted to try to figure out, because I know how x squared changes. Been playing with that for years now. Sine, how the sine function changes, what the values are at 3. So without a calculator, I decided to, at y prime of 3, figure out how that function is changing. And I think I came within 1/100th of a decimal place, which I was pretty happy with. So I encourage you to see that. It'll also strengthen your understanding of radian measurements. Now, through the lens of integration is all about different axes. So sine of x squared, right, is the function that we're trying to figure out the rates of change for. But when I put an x value in, it's not that number that I'm working with. I'm looking at what that number is after it's squared and where that is on the sine function. So all of that's done in the video. So I'll leave that up to you to look at. You're not going to make gains on it, conceptual and numerical gains on it. If you don't, I don't think, because I don't think you're going to see. I don't think you're going to see this out in internet land. So it's 5 or 10 minutes of looking at something. But if you're taking a calculus class, you want to understand what you're doing. You got to think about these things. All right. So the thing that I also was thinking about with respect to the chain rule was looking at exponential functions with it, because we really haven't looked at this function much, and we've got to start looking at it. And so in the Algebra 1 to Trig videos, the 50 videos there to bump up your foundation for this purpose, we changed exponential functions into E notation with just knowledge about a certain few e to the values. And e to the 0.7 is roughly 2. 0.69, but 0.7 is a nice round number to work with, and that's pretty close to 2 to the x, e to the 0.7x. And we have worked with the chain rule enough to know what its derivative is. It's e to the 0.7x times 0.7, which is what we are using as an estimate for the ln of 2. So the derivative of 2 to the x is, y prime is ln of 2 times 2 to the x. Well, let's think about this number, 0.7. That's telling me that I'm taking 7/10 of this function. 7/10, 7/10, 7/10. If I was doing 3 to the x, I'd be doing 1.1 times e to the x. Or 3 to the x would be 1.1 times 3 to the x, and that would be a representation of, I'm going to write it. Right? What I'm trying to say is that's ln of 3 times 3 to the x, and 3 to the x would be going up a little faster, and I would be a little bit above the 3 to the x curve each time to measure its rate of change. Okay, so if it's 7/10, then at 1, 2 to the 1 is 2, but the derivative at that instant is 0.7 times 2 to the 1. So if x was 1, right? And that looks like proportionality to me. That whatever this altitude is, that's 7/10 of it. Whatever this altitude is, that's 7/10 of it. Whatever this altitude is, that's 7/10 of it. And that tells me that we are fitting our model into something that looks like that. So if you see a problem like that, then you know you are looking at this situation, right? Because this is saying the rate of change of y is directly proportional to y. That's what I think I've just drawn there. I think I finally got this succinct statement. The rate of change of y with respect to x is a representation of proportionality. Okay? And so that might move the needle a little bit as far as the chain rule from another little perspective, but I highly encourage these two videos. Find the one where it's y equals sine x squared at x equals 3, and look at the chain rule through the lens of integration. This one I think you'll have to watch repetitively. Okay? And don't do it all in one sitting. Just look at it. Okay, it's a 5-10 minute video. Look at it. Shut it down. Come back the next day. Look at it. Shut it down. So on and so forth. And start to accrue. Okay, so integration, differentiation. Think of a loaf of bread. Think of one slice of the loaf of bread as a derivative. Think of integration as adding up all the slices to get the loaf. I was going to do a very quick, since it's an addendum, it doesn't hurt to get in an extra little practice. Let's see if you can nail all of these derivatives. And then I want to get to the last thing I said at the very end of the video. We're going to look at this problem from the context of our conversation. Let's move this back. We're going to look at this integration from the concept of conversion. All right. So, y equals x cubed, its derivative, 3x squared. You can pause the video. Do all of these real quick. I hope that they're in your pocket. Next one, 2/5 x to the minus 5/5, so minus 3/5. Derivative of 1 over x. I hope you don't say ln of x because that's the integral. You remember that we changed that to x to the minus 1, which becomes minus x to the minus 2, which is the same thing as minus 1 over x squared. A little practice with the algebra. Do you know what the derivative of secant is? I hope you're saying secant x tangent x. You're pausing each time. What's the derivative of tan x? Hope you recognize secant squared x. AB to the f of x. Kind of just did it. It is itself. Times the derivative of f of x times the ln of the base. So that's going to be f prime of x, ln of b. Boy, I butchered that. Right? What order should I do it in? I'll do it here. Derivative. So we have f prime of x, ln of the base times the ln of the base times the critter I gave you, a b to the f of x. All right. Derivative of sine is cosine. Derivative of cosine is minus sine. Derivative of the square root of f of x is 1 over 2, is probably, f prime of x in the numerator, 2 times the square root of f of x in the denominator. Okay, I did that one already. A e to the f of x, a e to the f of x. The derivative is itself times f prime of x. We do not need to write the ln of e because that's the number 1. Derivative ln of x, okay, I'm not going to do that one for you. That's a special derivative and we'll leave that for later. All right, now for the last conversation, conversion. Well, I forgot to write dx, sorry. If e to the 4x squared is in here, then it's got to be part of the answer. Inverse of what we just did over there. So this has to be part of the answer. And if you're good at taking that derivative, then you know that there should be a times 8x. Well, there isn't a time 8x. There's a time 5x. So how do we make that 5 turn into an 8? I think we have to get rid of that 5 and bring in the 8. And that's what we talked about. So maybe you can start doing these in your head. So therefore, we have 8/5 of what should happen plus C. And now I'm hoping that you followed that. And if you followed it and we keep practicing it, then you do it. There's no great brain here. Maybe I'm seeing some things because of the repetition. I threw the textbook out in 1993. I'm sorry, textbook people. All right, but learning it that way did not work for my class. They got the same final exam scores as everybody else, and they weren't good. Median was 80, and I don't think it was that hard a test. And a lot of students weren't writing the equational line. So I said, the heck with it. Either I retire then, and I quit, do another job, or I change the way I do things. And I changed the way I do things, and I started doing the equational line every single day for a minute. And I haven't had anybody miss it since 1993. One young lad last semester had a little trouble. All right, but everyone else on a final exam has quickly and easily written the equational line. And then what I found out is doing it that way, started seeing some things. All right, so I'm presenting it to you that way. I'm rambling. Another worksheet tomorrow.